In the gravitational potential energy at the top and the bottom of the first hill, the equation potential energy equals mass times acceleration due to gravity times the height was used. For the top of the hill, 3 meters was used as the height, which represented the top of the hill to the floor. For the bottom of the hill, we used 1.5 meters, which represented the bottom of the hill to the floor.
The acceleration due to gravity is 9.81 meters per second squared. The mass of the marble was 0.005 kilograms. We plugged both of those numbers into the equation, multiplied the mass times the acceleration due to gravity times the height, and for the top of the hill got a value of 0.14715 joules. At the bottom of the hill, we had a potential energy of 0.073575 joules.
To find the kinetic energy, we subtracted the bottom potential energy from the top and resulted in 0.073575 joules for the kinetic energy.
Because energy is conserved, we are able to subtract the two potential energies to get our kinetic energy.
Finding the velocity at the bottom of the hill.
To find the minimum velocity for the marble to travel around the loop, we use the equation centripetal acceleration is equal to velocity squared divided by the radius. The minimum acceleration that the marble has to be experiencing is 9.81 meters per second squared. The radius of the loop is 0.15 meters, and we're solving for velocity. After plugging all of the numbers into the equation, we result in a minimum velocity of 1.2 meters per second. To find the theoretical velocity, we use the equation V equals the square root of 2 times the kinetic energy divided by the mass.
We plug in 0.073575 joules for our kinetic energy and 0.005 kilograms for the mass of the marble. When you solve for that, you get a value of 5.4 meters per second for our theoretical velocity. Our actual velocity that we measured with the photo gate does not fall within our uncertainty. To find the kinetic energy at the bottom of the hill, we use kinetic energy is 1/2 mass velocity squared. So we plug in the mass of our marble, 0.005 kilograms, and the actual velocity of 3.73 meters per second. When you solve that, you get a kinetic energy of 0.034782225 joules. We use the equation total energy equals Q plus potential energy plus kinetic energy to derive the equation we use, Q equals potential energy minus kinetic energy. When we plug in our potential energy and our kinetic energy values, we get a Q of 0.038799275 joules. This value is the heat lost due to friction at the bottom of the first hill.
3, 2,
To find the apparent weight at the bottom of the loop, we solved for centripetal acceleration at the bottom of the loop, and it came out to be 92.75 meters per second squared. We plugged that into the force equation, being force equals ma, and the force, which is the apparent weight, came out to be 0.42 newtons. When we find the number of g-forces, it would be about 9.5 Gs when you divide 92.75 by 9.81 meters per second squared. To find the apparent weight at the top of the loop, we go through the same process, finding centripetal acceleration to be 36.5 meters per second squared, plug that into F equals ma, and we get an apparent weight of 0.18 newtons. When we find how many g-forces that is, we would divide 36.5 meters per second squared by 9.81 meters per second squared, which gives us 3.7 Gs.
Oi, crikey!
To the roof, everybody with me got their own parachute. You ain't scared of heights when you're sipping on booze. Party all night like I'm flying jet blue. You ain't never seen nobody get this loose. Shawty acting naughty with the body, what it do? Jump with this man, bump to this man, stump to this man, crump to this man. Got another hit man. Hold up, I wanna go up, don't wanna throw up. My click pull up, and every bad chick know us. That's the boy got us all feeling high. Master shawty on my ass roll 9. High rolling baby like I'm choking on pie. Super Bowl blimp, good year on top. Could I be a bird? I gotta be fly, butterfly and spur, and I got a couple words. We
With each stunt, we had uncertainty. In the first hill, we lost energy when the track bounces, which was in the form of heat energy. In the loops, the photo gate may not pass through the center of the marble, so that caused the measured velocity to be slightly off. In the hills, we had 2 hills and 2 valleys. We lost some heat energy because of track movement. The corkscrew was challenging. We found tight coils worked better to keep the marble on the track. The jump was a small jump, so it was fairly easy. The alligator mouth was kind of just for show, but because the marble is a projectile when it leaves the track, the hole in the alligator mouth had to be quite large. I hope you enjoyed your roller coaster in Australia.